This is exercise 21C. I chose question 4 to have a crack at so you can see me doing it. Yeah, so let's give it a go and see what happens. In this question, they're looking at angle between a tangent and a chord. They've indicated that, so there's your angle, right? There's your chord. Your chord is AC or CA. The angle from that chord is what we would say is that this angle at B is subtended by that chord. So you're looking at, right, just get a pen here, that point and that point, the angle has to come out from them to the edge of the circle, right? So you've got your tangent, you've got your chord, that's easy. You've just got to be careful. Sometimes there's other angles, you know, like, I don't know, for example, this one here. That's not what we're interested in. We've got to go from the chord and think, what's the angle that's subtended from that chord? And it's this one, right? Something that's sticking out at me, which might be involved in this question, I'm not sure, but this angle at X is also subtended by that chord, which is kind of nice in here. So this angle at B, these two angles, this one, we'll give it a name, we'll call it alpha, and this one here, they're the same angle because they're subtended from the same arc, right? So you've seen that as a different theorem. Maybe that'll come up in this question. All right, but I want to show you how I would do this in my book. And the first thing is I would copy down. Oh, wait, let me sweep. Sorry, I've got to actually draw a circle now. So when you're doing these questions in your book, can you please draw the diagram? Right, so it doesn't have to be a work of art. You'll see that me trying to draw circles here, it's a bit of a joke. Try and draw it as accurately as you can, but yeah, just make sure you do the drawing. And we had an X, a C, a B, an A. The A and the T I've put in, but I need this triangle here. So the C and the B, they've also got an X. They've put a center of the circle in. So they've got the C somewhere out here. They've got a B point. Maybe I'll put it there. I want it to be higher than the center. Maybe I'll put my center slightly lower. Put the B a bit higher so that this line can come above that center. They've also got an X up here somewhere. That's got to go to there actually. So they're going through there. And they're making a triangle ACB here. Right. And that last line was bad enough that I'm going to try and draw it again. Oh, alrighty. So yeah, it's not that pretty, but you want to get used to working with diagrams. So we draw diameter AX, done that, and we join CX. Oh, okay, we want to join this up too. Right, so just following the instructions. Find the size of angle at A. It's got to be TAX. TAX. Well, that's a right angle, right? So they've labelled this angle in here, the angle between the tangent and the chord, they've called it alpha. But because this is a diameter line, AX, and because this is a tangent, we've actually got a right angle here as well. So what's that? A1, and then they've got the angle at C as well. Oh, that's also a right angle. So, hang on. Just getting used to this setup. Let's get a grid backing. Might be a bit clearer. Alright, so this is A part 1. They say, what's the angle at TAX? TAX, they're writing it like that. It's the middle letter that gives you the angle. You could say, sometimes I write it like this. I say it's an angle, TAX. Right? So you've got to communicate this. And I would say that equals 90 degrees. And then I would explain to my reader how I know that. So I use curly brackets and I say radius tangent theorem. So this is one of your first theorems. Right? If you've got a radius of a circle anywhere, and then you've got a tangent, we actually proved this one in class, that this angle has to be 90 degrees. And I hope you're all watching this lesson because I want you to see what I'm writing down here. In your assignments, some of you are not writing this out, which doesn't matter too much, but when it gets to test time, it will matter. You need to be able to communicate your maths, right? You'll notice the book is doing that in the worked examples. So, for example, this next one, angle ACX, right? That's also 90 degrees. I need to communicate how I knew that, and it was because it's angle at angle of semicircle, angle in semicircle. I don't know, you can check the wording in your book. Theorem, right? So we're communicating our reasoning in brackets. We know that one of our first theorems, as long as we're going through the middle, we've got a diameter through the middle, we choose any point P, and we go to that point from the edges of the diameter, and we always get a right angle, which is what's happening here because they've told me this is the center of the circle here. I'll give it a label, O for like origin on a Cartesian plane. Okay, what's next? Back to the textbook. Oh, I've got it as a PDF, that's right. Here. All right, if angle at A, so it's TAC, is alpha, which they have labelled, find in terms of alpha CAX, CXA. Let me just write these down. So part B, they want angle at CAX, CXA, and they also want CBA. If I'm reading that correctly, which I think I am, CBA. All right, go back to my diagram so I can actually see this. CAX, CAX, so they want this little angle in here. CXA, where's that? CXA, we can work out that angle, which will be the same as alpha. And CBA, CBA should be coming out as alpha as well. Okay, so the angle CAX has to be 90 degrees minus alpha. I think this one's obvious enough that you don't need to show any explanation here. You've already explained it. TAX angle was 90, and then you've got your alpha, so this is just a matter of, well, what's left? It's 90 minus alpha. Angle CXA, right? We could work it out by considering this triangle ACX, right? We could say triangle ACX, right, obviously equals 180 degrees. So maybe I'd consider, right, we could say therefore angle CXA has to equal 180 degrees, that's coming from the triangle, minus away this 90 degrees, and minus away this little angle in here, which I've just worked out, is 90 minus alpha. Use brackets because you've got to minus the whole thing. Right? So you end up with 180 minus 90, well that's 90. Then you get 90 minus another 90, which is 0. So all the numbers actually cancel out to 0. And then you get minus alpha. Right? So it actually equals alpha. And to explain it, I think I've made it obvious by saying consider the triangle, but I could explain it at the end as well and say I'm just getting this from the sum of angles in a triangle. Triangle ACX, sum of angles equals 180 degrees. And this is what I'm worried about, is the communication. And in class, I'm not seeing people answering these questions properly, right? Now, when I come to the angle that we're actually interested in, I can go straight to saying it's alpha. And then I can explain why. It's angles subtended by the same arc. Subtended by same arc, right? So that's my explanation. What I've used there is a theorem that we already knew. So we've got some arc here. I'll put it in orange. There's my arc. I'll choose 2 points. All right. So let's call that, I don't know, angle A. And then let's choose another point. And we already know that those two angles are equal, right, because they're subtended by the same arc. We're using that theorem to prove this new theorem, right? Angle between tangent and chord. So what we're saying then is that this angle here is alpha, right? The arc is coming from AC. So we've got an angle there, we've got an angle there, they're the same, all right? Because they're alphas, oh look, you know, we started with alpha out here, angle between tangent and chord. So now we've shown that the angle between tangent and chord is equal. They're both alphas. Right? I might have to apologize for my terrible sketches, but I'm using this little pen that's, you know, not the best. Now I'm just going to double check the question, see if there's anything else we had to do. State the relationship, they're equal. All right. So TAC is here, TAC alpha, CBA, we found it, CBA. Right. We didn't assume the theorem that we were trying to prove at any point, right? Even though we were using other theorems, like we used angle in a semicircle theorem to find out that that was a right angle, we used radius tangent theorem, we used angles subtended by same arc, there and out to there, but we never used this theorem. We proved it, right? And that's the process that we need to go through. Okay, thanks.